we were discussing the concept of feature selection. So in particular, we saw that suppose we have a full data set like with different class levels, then like if we decide to split that data set on the basis of certain features, then like we may get a somewhat purer data set. That is, if we come return to the cat dog example which we are considering earlier. So first there were 200 examples, 200 animals which contain 100 cats and 100 dogs. Then what did we say? We said that we will split using one particular feature. Let us say can you hear me? Can you hear me properly?
Yes, sir.
Okay. So we saw that like we will consider one particular feature and that is weight. And specifically we considered a threshold also on this weight. So let us say something like whether it is greater than 15 or less than 15. Okay, so this is basically the question which we are asking. So if the weight is less than 15, so like basically there like we will focus on those elements of the data set for which the weight is less than equal to 15, and then separately we will consider those elements of the data set for which the weight is greater than 15. Okay, so now what will happen as a result of this? As a result of this, what we see is basically the data set has been split. That is, out of these 200 examples, we will see that 130 have come on this side and 70 have come on this side. Now, among these 130, we find that 85 are cats and 45 are dogs. Correct? On this side, 55 of them are dogs and 15 of them are cats. Okay, so now I can now my claim is that this split data set helps me to do classification in a more useful or in a more accurate way than what I could have been able to do earlier. Why? Because in this case, like I can say that like suppose suppose I come up with a classification rule like this. If the weight is less than equal to 15, then I will classify it as cat, and if the weight is greater than 15, then I will classify it as a dog. This is the simple classification rule for us. And we also saw that this gives us 70% accuracy. Why? Because in that case, these 85 cats are correctly classified, these 55 dogs are correctly classified. So total 140 examples are correctly classified out of 200. So we get an accuracy of 70%. Okay. Now, on the other hand, if we decide to split with the like using some other feature, such as say for example, another example which we considered is the color, right? So like we saw that if we split with respect to color, then there are three possibilities: color equal to white, color equal to yellow, and color equal to black. In these cases also, we saw some kind of split in the data set. Let's say if it is black, then it's 15 cats or 15 dogs. In case it is white, there is 30 here. In case it is white, let us say there are 120 cases here, out of which maybe 65 are cats and 55 are dogs, and then there are the remaining are the rest 50 are yellow, for which we have 65 cats, so 20 cats and 30 dogs. Right. So now, so this is the data set. This is one way of splitting the data set. This is another way of splitting the data set. Now it turned out that what we saw yesterday is that like this allows us to get 70% accuracy. But if we go for this kind of a splitting, then the accuracy will be much lesser, right? So like in this case, suppose in this case I decide to classify it as cat, because here cats are in majority in this case. So I can say that if the color is white, then I will classify it as C. If the color is yellow, then I will classify it as D. And if the color is black, then I will just flip a coin and classify it as either C or D. That is, for every example, I will basically do a coin toss and get and either classify it as a cat or classify it as a dog. Okay, so that means what? That means in this case, how many have I correctly classified? Here I have classified 55 cats correctly. Here I have classified 30 dogs correctly, and here let's say I have like an expected classification accuracy is 50%, so about 15. Okay, so 55 plus 15 plus 30, total how many I correctly classified? 100. So basically out of 100 I have correctly classified. Out of 200 I have been able to classify only 100 examples correctly, which is a only 50% accuracy, which basically means you have not done anything more than random classification. So as I said, that in case of binary classification, 50% just means I have done something random. It's not a class. It's not even worth calling it as a classifier. But in this case, I have actually been able to get a classification accuracy of 70%, which is not great, but at least it's getting the pass mark. So can we say something like that the split which we got in this case is somehow better than the split in this case? Can you pinpoint some property of this split which makes it better than this split? Yes, any idea? Why is it that this kind of a splitting, this 85-45 and 55-15, this particular splitting helps me to do better than this kind of splitting? What do you think is a big difference between this split and this split? Yes.
Hello, sir.
Yes,
Sir, am I audible?
yes, please. You are audible.
Sir, generally dogs are way more than cats. So
Where?
this this feature is more accurate than color feature, because color are more or less same as cats and dogs.
So like you are saying that like here in this group, dogs are more numerous than cats, so you can classify them as dogs easily. But in case of cats, but in case of color, you see that like both are
More or less
roughly
same.
okay, fine. Like you are close. So like, can you or someone else just develop this point a bit further?
So we have chosen a feature such that we create groups in which one of the class label will dominate the others. One of the class
Exactly.
label will be in larger amount.
Exactly, that is the point. So see here, so this when we consider this feature, we are able to split the data set into these two subsets. In each feature, in each subset, you see a dominant feature. Dominant class. In the original data set, no class was dominant. We had equal number of cats and dogs. But if we split this way, then one label becomes dominant. In this case, cat. In this case, dog. The level of dominance may not be same in either case. Like here, dogs are more dominant. 80% are dogs. In this case, cats are not that much dominant, but still they are reasonably dominant. But in this case, if we consider each of these subsets, we see that in neither case any class is particularly dominant. This is like just the same as the original case, that is to say it's just 50-50. In this case, cats are somewhat more dominant, but not much. In this case, dogs are a little bit dominant, but again, not much. So generally, in case of any data set or any sub data set, if one label dominates, then it helps us to classify that data set more clearly. Because in that case, like whichever is the dominant label, we will just want to classify all the examples as that level. So if the dominant level is like about 60% dominant, that is to say 60% elements of that data set belong to that particular label, then those 60% I will be able to classify correctly, but the other 40% I will misclassify. But if one label is say 80% dominant and the others are other labels constitute the remaining 20% minority, so in that case, if I label all of these examples by the dominant label, then I would have made a mistake on the 20% of the minority labels, but I would have got the 80% majority correct. Okay? So, so basically that's the idea. We need to choose the feature in such a way that we can make the data set, that is, we can split the data sets into subsets where one label dominates. Okay? So this kind of like one label dominating, this can also be called as purity of a data set. Purity of a data set means what? That is if one label, that is if the proportion of one particular label in that data set is high, then we say that the data set is more pure, is more homogeneous. And a homogeneous thing, of course, is easier to classify as opposed to a heterogeneous thing. So this is this kind of a subset has high purity or is homogeneous. On the other hand, these have low purity or heterogeneous and are hence difficult to classify. Fine. Okay. So now the question arises: how do we quantify these kinds of things as heterogeneity or homogeneity? Right? That is to say, in this case, like by looking at this split, the 85-45 split and the 55-15 split, like if we just see, we can understand that one like in this case, this is like we can say that in this case, basically this split is definitely more is definitely purer than this split. Okay. But how, like in other cases, it may not be that much obvious. Like for example, another case we considered like with weight only, if instead of 50, if we set the threshold to be some other value, then what happens? It may not be like we'll get another split, but it may not be that clear. Like in that case, I think like we had this kind of a split, 180 here and 20 here. Out of those 180, we had 100 cats and 80 dogs. In this case, we had 0 cats and 20 dogs. Okay, so like yesterday, I said that this is more desirable than this one because this is a smaller split. That is, and this like almost all the examples are coming into one bracket. That is, this is less balanced. But that's a subjective statement. How can I objectively or with the help of some mathematical quantity say or claim that this is better than this or this is better than this one? Okay, so that we have to somehow quantify mathematically if we have to develop the whole thing in the form of an algorithm. So the answer to this question is a quantity which is known as entropy. Okay? So basically, what does entropy do? Entropy tries to quantify the discriminativeness of a particular feature. As we said yesterday, we are looking for discriminative features. And different. So now, how do I measure which feature is more discriminating and which is not? The answer is this quantity called entropy, which we will study now. Again, this question, the entropy is a concept which many of you would have encountered in physics, chemistry, and maybe other subjects also. Like especially like when you are preparing for your JEE, I guess you would have come across this concept called entropy. Now, in this context, entropy is defined in the following way. So suppose we have a like a probability distribution like this. Okay, so let's say like a discrete probability distribution or a probability mass function, as one says. Before formally defining entropy, let me just give an intuition of it. So let's say we have a probability mass function over, let's say over 4 items. Okay, let's start with 2 items. Okay, 2 items. That means there are two, there is a random variable which can take 2 possible values, and each value has a certain probability of occurrence. So here is one probability distribution or one PMF, which is 0.4, the other is 0.6. Okay, there is a second PMF that is saying 0.8 and 0.6. Fine. Is this acceptable? Is this fine? What I have written?
Sir, sum should be 1.
Right. So the like in case for this to be a valid probability mass function, like what are like so what are the properties of a valid probability mass function? As someone already said, the sum of the different probabilities has to be equal to 1. And what is the other condition?
Between 0 and 1.
Right. It has to be between 0 and 1. So I'll make it as 0.8, 0.2. Okay. So here are 2 probability distributions available to you, P1 and P2. Okay. Now, which probability distribution do you consider as more informative? I have not defined what is meant by informative, but intuitively, like which probability distribution gives you more information and why?
Sir, second one, because if we predict, we will be 80% correct.
Correct. So in like here, that is as you said correctly, like here one class is has 80% or 0.8 probability of occurring. So like this is basically telling me that this value is highly likely to occur. This is not telling me much. It's saying that both values are roughly equal. This one has a slightly higher chance, but not much higher. In this case, you are telling me more clearly that yes, you are 80% certain that one value will occur only. So, like we can say that this probability distribution has a higher informativeness than this one. Which probability distribution has the lowest informativeness? There are 2 items, or the random variable can take 2 values. So in such a situation, what is the probability mass function which gives me least information?
0.5, 0.5.
0.5, 0.5, which means that both are equally likely to happen. So which has actually happened, or in a particular situation, I have no clue about. That is because I know that each of them are exactly equal. And which has the highest informativeness?
1 and 0.
1 and 0, either this way or this way. Both are fine. This is also telling me precisely that only this happens, this event happens. And this one tells me clearly that only exactly this event happens. So this is one extreme case where I have no information. these two are the other extreme case where I have all information. And these are extreme situations where I have some information. This has high information. This has low information. So this has the complete information. Complete information. So this has complete information. This has high information. This has low information. And this has no information. Okay. So this, like based on this concept, we define the this term called entropy, which is defined in this way. So like whatever is the minus this pi times log base 2 of pi, where pi is the probability of the ith value of the random variable being taken. So if we look at this one, so this one 0.8, 0.6, then what happens? I write its entropy as minus 0.8 times log base 2 of log base 2 of 0.8 minus 0.2 times log base 2 of 0.2. Right? So like this is how you can calculate the entropy in this case. Now what happens in this case? There might be a bit of a trouble. So we have minus 1 log 2 1 minus 0 log 2 0. Now we know that log of 0 is not defined, but fortunately we don't have to worry about it either, because this is anyway multiplied by 0. So we just like whatever this is, even if it is undefined, we just ignore it. We put it as 0, and this is minus 1 log 2 1. So log of 1 is of course 0 itself. So we write 0. So we can say that in this case the entropy is 0. In this case, we will get some value of entropy. In this case, like you can calculate that this entropy is going to be the highest. So in this case, this will be the entropy. You can actually work out what how much the entropy will be. Can anyone tell what is the entropy in this case? Quick, you have cracked the JEE. You should be able to do this very quickly.
Minus log 0.5.
Minus log 0.5. So in other words, simplifying it further,
Minus 1 for the 1.
so instead of 0.5, I write it as this. So I write log 2 base 2. So you get okay. In some, now this taking this log base 2 is not necessary. Like if you take log base 2 in this case, of course you will like it makes sure that this entropy lies between 0 and 1. So in general, if instead of two things, if you have of course in this case the random variable takes two values, so you take log base 2. Like if you have to consider k values, that is to say like in case of these class labels, if you are consider a k-way classification problem, then you may have chosen the base of this log to be k instead of 2, whatever that k is, and so as to ensure that your this thing, your entropy lies between 0 and 1. So instead of these two classes, like suppose I had 5 classes, right? So obviously in that case, what will be the most discriminate or the most informative PMF? Of course, it will be any one of these things, either this or this, etc., etc. And which will be the least informative PMF in this case? which will have
Point two.
where all of them have equal probability, that is 0.2 each, right? So you, like you can work out the entropy that if you like in this case, that is if you are taking say -2 log 5 base 0.2. Okay, so then and you just like add up over all these things. So this first 0.2 will go away because you are like multiplying the same thing. So basically you will get minus log base 5 of 0.2, which is 1/5. So that works out to be this minus comes in, you get log 5 and you get 1. Right? So basically, this by taking the base of the log to be the number of values which this k can take, you can ensure that your entropy will lie between 0 and 1. So that 1 means the least informative situation where you have no information at all, and 0 means the situation where you have complete information. Now, not that having 0 and 1 on the two sides helps. Like if instead of taking k as the base, you could have taken 0 the e or 10 or anything as the base of the log also. It would not have made any particular difference. So in general, the what we can say is that for classification, that is on one end of the spectrum, we can have low entropy. On the other end of the spectrum, we can have high entropy. That is, so for the purpose of classification, what do I want, low entropy or high entropy?
Low entropy.
I want, so low entropy means more information. Low entropy is equivalent to high information. And high information means good classification. Okay, so now if you actually work out the entropies that we get in this case, so this one, like if you consider the entropy in each case of each of the data sets, you will find that initially this data set, of course, like we saw as high entropy, which is 1. Okay, this was the initial entropy. Now here, if we consider this data set, we will consider some lower entropy. Let us say something like 0.3. Okay. I have not done the calculation, but let us say it will be something like 0.3. On the other hand, if we consider this one, this is an even purer data set. So let's say this has an even lower entropy of something like maybe 0.15. Okay. Now then, what I am saying is that I initially had a full data set of entropy 1. I am splitting that into two smaller data sets. One has entropy 0.3, the other has entropy 0.15. Okay. So, and additionally, we also need to consider the fact that like it may happen that there is one subset which has low entropy, but that's purely because it has a small number of elements present in it. Because like in this case, for example, this is pure, but it is also small. So we have to somehow take the size also into account. Okay, so now what do I do is that I define a term known as the information gain.
Sir.
Yeah.
Please go to the slide, sir, 1 second.
Yeah.
Sir, here, sir, in the color features, sir, for white color, sir, there are 66 cat and 55 dogs. Sir, for the majority 66 would be, sir, written as here, but you are written 55, sir. I don't get it.
Sorry, just a second. Yeah, so thanks for pointing that out. This will be 65 correctly classified. And this is, yeah, so, that was right. Thank you. Thank you for correcting. So 65 are correctly classified. Here 30 are correctly classified, and here like expected 15 are correctly classified. So okay, not 100, but 110 are then correctly classified. Thanks for pointing out. So we get 55% accuracy, which is still very low.
Hello, sir.
Yeah.
Sir, for certain events, I think there will be less information compared to the events which have some probability, right?
Sorry.
For some certain events, like a probability one, that
Oh.
event will have less information compared to event which have some probability, right? Like sun rises in the east, which has a less information, right, sir?
There is, see, it is telling me that it is telling me clearly what is going to happen. See, what I need to do is I need to predict. So suppose I want to predict that which way the sun is going to rise tomorrow. Okay, now like if I have so basically I will want to maximize my chance of getting it correct. So suppose from my data set tells me that in one case my data set tells me that there is 0.8% chance that it will rise in the east and 0.2%, 0.1% chance that it will rise in the north, and there is 0.1% chance that it will rise in the west. This is one situation. The other situation is I have been told that there is probability 1 that it will rise in the east and everything else is zero. Okay, so this one is clearly telling me that clearly specifying to me what is going to happen. So if then I can say with full confidence that yes, it is going to rise in the east. In this case, I am not able to. That is that is whatever prediction I make, I will probably not be able to get it 100% right, because if I say that if my prediction is that it will rise in the east, there is a 0.2% chance, there is a 20% chance that I may be wrong also. So I may make a mistake. But in this case, if that is assuming that my data set is representative, I am guaranteed to make the correct prediction.
Yes, sir, but the remaining sites also have some probability, right? So there is much information than compared to raising at only one side.
See, by information, that is
Information.
by information I mean certainty. That is that of course, it is that is the kind of information which will be useful for me is only is if one if it enables me to make a robust prediction. It does if it does not tell me anything give me information about other possibilities, I am not very concerned about it unless it hampers my prediction capability. So as I was saying that let us consider this particular so based on the notion of entropy, let us now define another feature another thing another concept known as information gain. So what I was telling earlier in the previous slide was that initially I had a data set with high entropy. This one with 100 cats, 100 dogs. This has high entropy. With after splitting, say into 85 cats, 45 dogs, and 15 cats, 55 dogs. In this case, we saw that I have got low entropy. But this one, but I have earlier I had one single data set. Now I have got two data sets, that is two subsets. So that is to say, I may be interested in understanding here. So we can say in this case I have got one has got low entropy, this one has got medium entropy. So now I may be interested to find out how much I have been able to lower my entropy from here to here. How much has the entropy been lowered? Now I cannot do a direct subtraction because this has there is only one thing here and there are two things here. So I will have to make a weighted subtraction. That is to say, and what will be the weight? The weights are going to be the sizes, the relative sizes of the data set. So this has 200 elements. this one has 200 elements. This one has 130 elements, and this one has, of course, 70 elements. Now, small and that is a small subset being pure is one thing, but a big subset being pure is carrying a more robust information to me. That is, if a small, like if I have observed only one or two cats which are like say white in color, it does not necessarily tell me, like on the basis of that I cannot make a strong statement that if I see any white animal, it is a cat. But if I have seen 100 examples which are white in color, and out of them 90 of them are cats, then I can be more or less confident in making such a statement. Right? So the only the purity does not matter. The size of these subsets also matters. So that is why the information gain is defined in the following way. So let us say N is the like the set of that is, sorry, capital N is the size of the original data set. Now, like with the help of a feature, I have divided it into let us say k number of states, or say L number of states, N1, N2 up to NL. Okay, in this case, of course, L equal to 2. So that means what? That means N1 plus N2 plus N3 all the way up to NL is equal to N. That is, all the N examples I have divided into these many subsets. Okay, so now I can, and each of these subsets, so let's say that H is the entropy of the initial or the original data set, which is a high. Okay, and each of these subsets, they have their own entropies, say H1, H2, all the way up to HL. Fine. So now I can say that the information gain is basically the reduction in entropy. This I define as H, the original entropy, minus N1 by N times H1 plus N2 by N of H2 all the way up to NL by N by times HL. So basically I have initially I had the full entropy. Here I am taking the weighted mean of the entropies of the different subsets. Okay, makes sense? Instead of considering like H1, H2, etc. separately, I am just taking an average of these, but not a direct average, but a weighted average. Why? Because that is I want to give more weightage to those splits which are larger in size. Right? So this is the definition of information gain. Now, so now, like if I ask, like if it is asked that if I want to do a classification, on the basis of which feature will I do the classification? That is, which feature I will call as the most discriminative feature? The answer is that whichever feature gives you highest information gain gives maximum ISG information gain, that feature is most discriminative. Right? And it is not only the feature which matters, the way you split the feature, that also matters. So like for example, like we say that the weight feature that yesterday we had said that has 25 values, 1 kg, 2 kg, all the way up to 25 kg. So 25 values this weight feature can take. Now I can split the weight feature into 25 different ways. Okay, so like I can consider that that is N1 that is L. I may go for L equal to 25, which means that N1 is the set of all examples which have 1 kg. N2 is the set of all examples which have 2 kg. N3 all examples which have 3 kg. NL all examples which have 25 kg and so on. This way, this is one way of splitting it. Another way of splitting it is, as we are discussing here, the 15 kg threshold. That is lesser than 15 kg or greater or sorry, less than 10 kg or greater than 10 kg. So that is another way of splitting. A third way of splitting may be say greater than 20 kg or less than 20 kg. Yet another way of splitting may be 1 to 5 kg, 6 to 10 kg, 10 to 15 kg, 15 to 20 kg, 20 to 25 kg, and so on. This is so that will be a situation of 5-way split, L equal to 5. And the splitting need not be uniform either. I may go for 1 to 5 kg, 5 to 13 kg, and say 13 to 25 kg. This kind of feature splitting also I may consider L equal to 3. So it is not just feature but also the split plus whichever feature plus splitting gives maximum information gain, that is that most discriminating. Okay, so that is whenever, like when we are trying, like when we have got a data set and we actually want to split the data set for the purpose of classification, this is what we will have to do. First of all, choose the feature and its corresponding split, which gives us the highest information gain, and then do the splitting accordingly. Okay, so this is the way we build the decision stump algorithm. So finding out which feature, so then of course the number of features can be quite high. There are capital D features, and then each feature can be split in quite in a significantly large number of ways. That is, so like as you can see in this case itself, in the like there are 25 values, so like there are so many different ways in which I can split this feature. Similarly, the color feature, which has takes 3 different values, like either I can go for this, so color feature, like we saw that it takes 3 values, white, yellow, and black. So either I can go white, yellow, and black separately, or I can put white and yellow in one bucket and black in another bucket, or maybe white and black in one bracket and yellow in other bracket, and so these kinds of things also I may do. So basically, we not only we have to go over all the D features, but we may also have to go over a large number of splits for every feature, which is of course quite difficult to explore. So that is to say, finding out this kind of a splitting is often a non-trivial task, and we often have to use various kinds of heuristics in finding what can be the optimal way of splitting. Now, so basically, so then what is the algorithm of the classification? The classification algorithm is nothing but take the data set, evaluate the initial entropy, explore the different features and the split, which gives us the best entropy, the best information gain, and then choose that like that feature and that split as the basis of your classification. So so what is the like benefit of that? So basically, each discrete feature, it splits the data set. Now, if the features are continuous or real values, they can always be converted to discrete values by what is known as binning. Now, when like a pure data set, which we are talking about earlier, is a data set which, as we said earlier, it has a data set we call as pure if one particular label is dominant in it. In other words, it has a disbalanced class distribution. It's not that the different classes have roughly equal probability like 0.5, 0.5 or 0.2, 0.2, 0.2, 0.2, not like that, but it is closer to the 10000 case. Or it need not be exactly 100, it can be 0.9, 0.1 or 0.8, 0.1, 0.1, something like that also. But I want a pure data set which has a disbalanced class distribution and hence a low entropy, and hence it provides me high information gain with respect to the original data set. So we can choose that feature which provides the highest information gain. So this is what we call as a decision stump. If we consider yesterday's example of camera rating prediction, so this was the route which has 100 examples of the ratings given by the customers. 63 had low ratings and 37 had high ratings. Now, if we go for the company feature, company C1 and company C2, here in this case we get a split which has 54 elements, and here we get a split which has 46 elements. Right? So the 54 element split, we see that one level is dominant. So we so the classification we do as follows: whenever there is whenever we see any example having C1 as its company value, we just predict it as the ratings to be low, because that is the dominant thing, the dominant level of this subset. On the other hand, if we find the label to be C2, the company to be C2, we in this case predict that the rating is going to be high, because high is the dominant level in this case. Okay, so we see that so this is basically the decision stump algorithm. Now, of course, this is assuming that C1 this splitting with respect to the company feature has the highest information gain. So the calculation I have actually shown in these slides, which you can these slides are put up in the file section, so you can just go and check these calculations anytime. You can see that among the different features that are considered, this company feature has the highest information gain. So I have split it in this way, and I am getting about 70% of accuracy. Okay, so this is the decision stump algorithm. Now, I may not stop at splitting the data set on the basis of one feature only. Even after I have split with respect to the company feature, I may continue to split further on the basis of other things. Okay. Say let us say another feature that we considered, let us say the price feature. Okay, so company C1, okay, fine, you will get it seems that company C1 always gets low ratings. But but is there any difference if I between the high cost examples from company C1 and the low cost examples from company C2? It may be, it may not be either. But whatever it is, we can actually try to make such a split and see if it helps our classification in any particular way. It turns out that in this case also it does not help us. But if in this case, that is among the ones with company C2, if we now again further break it up into the low cost ones and the high cost ones, then can we predict better? It turns out that yes, we can do. Those elements which which are from company C2 and which are costly usually get low rating. Maybe of course the number of examples is smaller, but still it seems that low rating is dominant in this case. But while among them, the low cost ones from company C2, it seems that the high ratings are dominant. That is more dominant than they were if we did not consider this price feature. Okay, so you can see here that if we had looked only at the C2 level, only at the that company level, and then on seeing the company level at C2, I would have predicted high ratings. But that would not have given me a lot of accuracy. The accuracy would have been 26 out of 46. But if I can now classify them further, that is after company, if I look at price also, then I will be able to get higher accuracy by classifying a higher number of examples correctly. So how many do I correctly classify now? Yes. Earlier I was correctly classifying these 26. If I did not have this part, if I had stopped here, then on the basis of like if we are doing like this, then whenever I saw the level as C2, I would have predicted y equal to high. So I would have got 20. That is, there are there are 46 examples here. I would have got 26 of them correct. So I would have got an accuracy of 26 by 46, which is say about 55%. But in this case, how many am I correctly classifying? Being able to correctly classify out of these 46?
30.
73.
That is, these 25 I have correctly classified, and these 5 I have correctly classified. So 30 I have correctly classified, and there are 43 this side are correctly classified. So like in this case, I am able to get an overall classification accuracy of 73%, which is higher than the 69% I had earlier. Okay, so that means that instead of split, so this is what we had done for the decision stump algorithm, that is split with respect to a particular feature and stop there. But if we go on splitting with respect to other features also, I may be able to get higher accuracy. So on what basis will I split these features? That is, so like so initial data set is this. Now what I did is I explored the different features and I saw which particular way of splitting is giving me maximum information gain, and I split with respect to that. Now each of these subsets I can again split further on the basis of information gain only. That is, here, like if we consider all the examples here, then this C1, this company feature, this has gone away because all the examples lying here have the same company C1. Right? So now the company feature is no longer relevant to us, but there are still more features to consider. Total capital D number of features were there. One has been selected, but the remaining D minus 1 are still there. So now out of these D minus 1, I may be interested to find which is the next discriminative one with respect to these examples. So whatever that is, I can split them with respect to that feature. The same thing I repeat here also. Okay, so that is at every point, whenever you have this kind of a data set, a subset, you will always want to consider if you can split any further or not. It may happen that you cannot split it any further while with any significant information gain. That is, whatever features you are selecting for splitting is not giving you any particular information gain or some very low value of information gain. In that case, you may consider stopping. You may not split the features any further, and you can just stick to what you have already have. Alternatively, you can just go if you see that there is some way of splitting which is giving you information, then you are welcome to split further in that case. So by this way, what we get is what is known as a decision tree. By tree, this in PDS class you would have studied, like this is basically what a tree looks like, a tree data structure looks like. So initially we don't have any information about the level, so we first ask this question. That is when we are. So what is the classification algorithm? Basically, the classification algorithm is that you get an example. You first look at one feature, let's say feature number 1. Based on feature number 1, you decide which way to go, this way or that way. Then, supposing you have done this way, then you query the next feature. Let's say you go for feature number 6. So then, you query, okay, feature number 6, which way should I go, this way or this way? So that you will have to choose accordingly. Now, why is it that I first went for feature number 1, then for feature number 6, and maybe after that I will go back to feature number 3? Why is this particular sequence? Now, this is a sequence which gave me highest information gain on the training set. That is the sequence in which I will have to split the different features in their respective orders of importance. That is the sequence is what we learned during the training phase, and we utilize it in the testing phase. So because we take a tree of decisions like this, a sequence of decisions with branches like this, that is why this algorithm is called decision tree. So what is the decision tree algorithm in a nutshell? In the training phase, we identify the feature that results in maximum information gain. I mean, not just feature, but it's split also. So you split the dataset accordingly. Now identify any feature which that can result in further information gain on the split set. So this is the original dataset. This is these two are the split sets. So see if you can find any feature which can split these subsets even further. If yes, then split further, and if no, then stop. So if you have decided to split them even further, then again, so you'd have got new nodes like this. So this subset is split into this one and this one. So now what you will do? You will again go back to step 3 and see if these also you can split any further based on some other features, say frame rate or picture resolution, something like that. Okay. See if that gives you information gain. If yes, then you split that and again try to continue further. And if no, then you just stop. Okay. And when you finally stop, then what you have got these leaf nodes in the tree. For example, in this case, these are the leaf nodes. Assuming that we have stopped here, there is no further splitting to be done. So these are all the leaf nodes. So in each leaf node, your prediction is going to be the modal level. What is modal level? More like mean, median, mode, you know. So whichever, so basically there is each subset defines a frequency distribution of the class levels. So whichever level is the mode of that distribution, you use that as your predicted class level. So this is the decision tree algorithm. And so with that, let me take a break now for 5 minutes. And after that, again, we'll discuss this further.
Sir. Sir?
Yes, please.
Sir, in point 3, you told further information gain. That means until delta H is not 0, we have to split, right?
Sorry, in point 3, identify if any feature can result in further information gain on the split set. Further, like information gain means like suppose there is some information gain may be there, maybe 0.1, 0.2. Like what I really mean is whether there is a significant amount of information gain. Like if yes, then I will stop. If no, if yes, then I will split. If no, then I will stop.
So like significant means what? Is there any measure? How much value?
So that is a threshold. That is a parameter which the users define. There is no like strict measure on that.
Okay, sir.
Sir,
yes?
Sir, information transformation and information gain are totally different, right?
Yes. In this case, we are talking about information gain.
Okay, sir.
We will resume after another 5 minutes.
Sir, for step 1 and step 2, like, should we have to iterate over all the possibilities?
So ideally yes, but all the possible doing that may become difficult. That is the features, of course, capital D features are there, and then each feature can be split in many ways. So that is, it may not be possible. Practically it may not be possible to consider all the possibilities. So you will like as engineers, you will have to come up with some understanding of what can be reasonable. That is, you may think that like one way is that you will consider only binary splits. That is, every feature you will split it as greater than this value or less than this value, something like that. So that is one way of like one approximation which you can do. Other approximations also you may do depending on your feature engineering skills. So yeah, the short answer to your question is yes. Ideally, you should do that, but then practically it may not be feasible. So you will have to find some ways of approximating it.
So, sir, you are saying like we have to split it into two types, greater than, less than. So
I am saying that is one possibility.
yeah, it's
I'm not
yes,
saying it is the only possibility.
yeah. So like if you are like estimating that greater than, less than, like we should have to like iterate, like we should have to iterate the data set, like to find
Yes.
the
Yes, that you have to do.
Sir, how to find the information gain in doing like after two splitting? If you can
How
repeat once. How to find information gain in more than one splitting is there?
okay. In more than one state, like I mean, you know, like are you trying to say something like this? That is, so this is my original data set. Now this I split in this way. So let us say this is the first split, and then let us say that here is the second split. So here I have split into three ways, right? So like is this what you are asking? How to calculate the information gain in this case?
Yes, sir.
Okay, so here this one has some entropy. Let us call that entropy as H naught. And so this has n naught number of examples and H naught entropy. Now after splitting it, I have this one has n1 examples, this one has n2 examples, this one has entropy H1, this one has entropy H2. Okay. Now when I split this even further, I will get entropy H3 like examples N3, N4, and N5, N4, N5, and entropies here H3, H4, and H5. Okay. So now the information gain here you will like calculate as follows. Just imagine, like forget all these other things. Just consider information gain as H1 minus N3 by N1 times H3 plus N4 by N1 times H4 plus N3 by N5 by N1 times H5. Okay, so this way you'll get the information gain for in this particular case. Similarly, this H2 again, if like if for a proposed split, you can calculate the information gain like this.
We can't find like the overall information gain.
No, information gain is not something which is done overall. It's like that is okay. That also you can do, but it's not part of the algorithm. The algorithm goes step by step. At every that is like once you have any data set, you split it into subsets on the basis of information gain. Then each subset you may choose to split further based on information gain locally with respect to that one. There is no such thing as you will calculate the overall information gain and then decide the entire split all in one go. That is not how it works.
Okay, sir. Okay, sir.
Okay, fine. Let us now resume. Just give me a second. Okay. So let's resume now. So so this is the decision tree algorithm. So this is how the training phase. Now what happens in the testing phase? Now in the testing phase of the decision tree algorithm, we get an example which has of course has certain features. So what you do is you just follow the sequence of decisions based on the features of the test example, and accordingly you make the prediction. So if we look at it, so let us say that this is the decision tree that was built, right? This is the decision tree that has been built on the basis of the training set. Now what am I doing? Now now a test case has come whose a camera which is manufactured by company C2 and whose price is $350. So now how do I classify it? So first, like right now, initially it has no information, so I place it here in the root category. Now you at this point these numbers do not matter. So you just put it in the root category. Now you have already decided based on your training phase that you will look at it company C1, the company, if the company C1 will go this way, if the company C2 will go this way. So your company is C2. Okay, so you take it, so you go here and you like you place it in this subset. Next, what do you do? Next, you look at its price, whether the price is less than 500 or greater than 500. It turns out that its price is $350, so it is less than 500. So you place it in this subset. Okay, now it turns out that this subset is the leaf node. That is, there is no further splitting to be done. So whenever there is a leaf node, like the prediction is going to be the modal level of this leaf node. So what is the modal level of this node? That is high, H, that is high rating. So you predict that the rating is going to be high. This is how basically the decision tree algorithm for classification works. Okay. So now this guy like like as I said earlier also, this it need not be just one like binary classification. It can be like multi-way classification also. That is, instead of having only two categories, only two labels as low rating and high rating, we may actually go for the individual kinds of ratings also. That is, so that is whether the rating is going to be 2 or 3 or 4 or what, that also we may want to predict. So in this case, so let us say with respect, so this was the root where these were the different frequencies of the different ratings. So now if we split with respect to company C1, we find that this is the frequency distribution of the different ratings, and if the company is C2, then this is the corresponding frequency distribution. So as I said, we have to go for in the leaf nodes, we have to go for the modal level. What is mode of a frequency distribution? We know that mode of a frequency distribution is that value for which the frequency is maximum. In this case, which has the highest frequency? Obviously 2. So I will predict y equal to 2. In this case, which has highest frequency? Obviously 4. So here I will predict 4. So then, like but that is to say, in this case, so what is the accuracy I achieve in this case? So there are 18 here which have the level of 2, and I have correctly classified and I have predicted 2 also. So so like although the total number of examples here is how much? 15 plus 18, 33 plus 10, 43 plus, okay, so 54 are here. So out of these 54, like 18 of them belong to class 2 and 15 of them belongs, like here 15 of them belongs to class 4. So these 18 and these 15 I have correctly classified. So I have got an overall accuracy of 33 out of 100. Okay, now again, this 33 out of 100, as I said, it's a low number, but given that this is not a binary classification problem, this is in fact a 5-level classification problem. So here a random classifier would have given, is expected to give us accuracy of how much? Yes?
20%.
20%. So like just like in case of a binary classification, a random classifier would have given me 50% accuracy. In this case, a random classifier which just uniformly predicts some class level, that would have given me a class accuracy of only 20%. Compare, so 33% accuracy is not great, but at least compared to 20% we have gained. So it's not such a bad classification also. Another thing which I could have done in this case is I could have like if I had not split at all and if I had just gone with the prior distribution, then I would have chosen the modal modal level of the original data set. What is that? That's again 2, because this 24 this has the highest frequency. So in that case, what would have my accuracy would have been? Obviously 24 out of 100, that is 24%. These 24 I have gotten correct, everything else I have gotten wrong. So that I have got 24% accuracy. So a random classifier 20%. This frequency just prior frequency based classifier 24%. With first level of splitting, with one level of splitting 33%. So we can see how the classification accuracy is gradually increasing. It's possible that if I am able to split these subsets with respect to another feature like say price or maybe video rate or something like that, maybe it will increase even further. Right? So generally going for higher splitting is generally more useful till a point. So here are some of the advantages and disadvantages of this decision tree algorithm which we considered. So first of all, it is easy to interpret. Right? That is to say, like what we have done is basically a rule-based classification. We have a sequence of criteria. Each of these are basically a criteria. That is, I am evaluating a sequence of criteria one after another. Like if one criteria is satisfied, then I will look at another criteria. If the first criteria is not satisfied, then I will look for yet another criteria and so on. So basically, I have a chain of criteria to be followed, and the criteria are also fairly straightforward. Each of them is just based on the values of the different features. So it is very easy to interpret, and testing is really easy. We just need to, for any testing example, we just need to evaluate its different features in a particular order. So just if the depth of the tree is high, that means I'm sure you know what is meant by the depth of a tree. You have all studied PDF. So whatever is the depth of the tree, that many calculations or feature computations I have to do. In this case, if I say that the height of the tree is 2, then that means I have to do 2 calculations. First, my first calculation is to check the value of feature of the feature called company. Our second thing is to check the feature called price. Okay, so the testing is really easy. I just have to do these 8 number of calculations. The calculations are also very easy to do. So based on that, the classification, the testing time is really efficient. And finally, it is also useful because it provides a ranking of the features according to usefulness. It gives me a clear understanding of which feature is more useful, which feature is less useful, etc. etc. The features that on which I split initially, this is the most useful feature because that is the one which gave me the maximum information gain on the original data set. Then after that, I will go for features in the order of their importance. Whichever is able to give me the highest information gain at any stage, I am choosing it. Okay, so basically what I have done is I have got a ranking of the features. So so total capital D number of features I had. Now it may happen that capital D is very high. I cannot handle so many features. I have a computational resources, limitations of computational resources. So unlike in K-means, where I had to do all the computations or all the distance calculations in the full D-dimensional space, in this case, what I have done is I have given you a basis in which some of the features can be done away with. I may not need all the capital D features at all. In fact, it may happen that capital D equal to 500, but only 5 features are informative. So this decision tree framework is actually helping me to identify or to rank all those features in a particular order so that I can choose them according to how many, whatever I can afford. If my computational requirements are such that I cannot do any more than 3 features, then I know which are the features to go with. The features which the top 3 features which I have got in the decision tree. If it turns out that only one feature I can deal with, then of course I will go with the most informative feature, the one which gave maximum information gain, and so on. So this decision tree gives us a ranking of the features according to their usefulness, and which in turn enables me to do the feature selection as far as my keeping in mind my computational requirements. Okay, so these are the advantages of the of this particular algorithm. Okay, what are its disadvantages? Okay, one operational disadvantage is that something which we already discussed. Evaluating all the possibilities or all possible splits of all possible features is often computationally intractable. That is, especially if some of the features are real valued, then where to put the threshold or how many thresholds to put, into how many bins or buckets should I divide each particular feature? There is no answer to this question with any solid mathematical basis or algorithmic basis. I will basically have to try out different things according to my domain knowledge and engineering skills and come up with an answer. So that is an operational difficulty with this difficulty. Apart from that, also these are the following disadvantages. First of all, no optimal solution is known. I have decided to split the data set with respect to a particular criteria called information gain, the one which gives me the maximum reduction of weighted entropy. Right? That's what we said in the algorithm. But after all, information gain is just a heuristic. Why am I can I actually make a claim that this, that is maximizing the information gain is guaranteed to give me maximum classification accuracy also? So here it turned out that when I split in this particular way, I got an accuracy of 69%. How did I choose this particular split? On the basis of information gain only. I considered some alternatives. Among them, these alternatives gave me the maximum information gain. So I decided to split this way, and I got this much accuracy, 69% accuracy. But is it possible that there is a higher accuracy can be obtained by splitting the data set in a different way? We cannot rule out that possibility. That is, information gain is one criteria, but it's not proven that this is the only criteria or that this is the best criteria. There are other indices also, like there is something known as Gini index, on the basis of which some people do the splitting. Right. So instead of entropy, there is they use another criteria called Gini index for the splitting. So can we say that this is the best, that entropy-based information gain is the best criteria, or the Gini index gain is the best criteria? Can we say something like that? No. Whatever works, these are all heuristics which people have tried, but nobody has proven that under such and such conditions, this is the heuristic to go for. That we do not know. And also, if the tree becomes too deep, then that is to say, that is here, of course, this is a tree of size of depth 1, this tree of depth 2, then if I want, I may want to split these features even further and make it depth 3, then depth 4, etc., etc. I can do all those things. But that results in a particular problem known as overfitting. Now, what is overfitting? So we will come to the concept of overfitting a bit later, but I can explain to you intuitively with a simple example. Overfitting, like let us consider the situation where a student is learning a particular subject. Now, so say the examples that the student has got, the training examples the student has got, let us say, is like worked out solutions to some problems. Let us say, for example, you are preparing for your JEE, you are trying to understand why or trying to study one particular subject, let us say thermodynamics. So you have got in your like in your textbook, in your physics textbook, which you are studying, you have got say 20 worked out examples or worked out problems with respect to thermodynamics. Okay. By the way, what are some of the physics textbooks you studied for your JEE?
Halliday.
Resnick Halliday.
H.C. Verma.
H.C. Verma. Oh, okay. Okay, so these were the books we also used to study in our times. It was like say more than 15 years earlier. So I was just curious if the same textbooks are still used. So it seems that they are. Okay, no, whatever. So let's say that 20 examples, worked out examples you have got. Now what you do is you just memorize those 20 examples, the worked out examples. That is, you just memorize the question and you memorize your answer. Okay, so if that happens, then so what is the disadvantage of doing it? Obviously, the disadvantage is that if you get now in the exam, if a different question comes, which is not the same as any of those worked out examples, then you will not be able to solve it, or you will do a bad job of solving it. Right? So this kind of a situation is known as overfitting. So to prevent such overfitting, that is not what you do, right? That is if you are given 20 worked out examples, you probably do not memorize all of them. What you do, you just maybe the first 10 of them you see, you form your own, like you form some idea in your mind that how these problems are solved. That is to say, that is, we can interpret that as you basically learn some kind of a model which maps from the a question to an answer. Like a problem from the problem space, you learn a mapping from the problem space to the solution space. Now, of course, the problem space in this case is highly complicated. You may not be able to represent it by a vector space. Similarly, the solution space also may be highly complicated. But just make a say for the time being. Like let us say that when we can say that what you have done in that time when you just saw those 10 worked out examples and formed an idea, we can say that basically you formed some kind of a model to map a problem to a solution. Then what did you do? You then try to test yourself. Let me see how well I can do on the 10 remaining problems. You try to look at the other problems and you try to solve them according to the model which you have built on the basis of the first 10 examples, right? And then you will get some answer in each case, and then you will tally that answer with the solution that has been given. If some changes have to be made, suppose you see that you have made a mistake, then you will have to update your model accordingly, and so on. So that is what you usually do. But that is the correct way of, in case of machine learning also, that is the correct way of doing it. That is, you use part of the training set to build a model, and then you see how good the model is by testing its performance on the rest of the data set. Alternatively, what you can do is you can build such a model which will be able to reproduce every example or make the perfect prediction for every example in the training set. But if you give any example outside the training set, it will not be able to do any classification at all. So that is what we like. That is the intuition behind overfitting. The formal definition of it, of course, will come at a later lecture. But let us say that like if we build a decision tree which is very deep, then what happens? That is essentially akin to memorizing the problems or solutions to problems, in which case you are likely to suffer from overfitting. So you do not utilize all the information that has been given to you. You never try to like make yourself perfect on the training example. Rather, you leave some space to generalize, so that even if the your performance on the training set is not perfect, you always have a scope of doing well on the testing set or on the validation set, whatever. Okay. So that is basically what this decision tree algorithm is all about. Now, this decision tree, as we saw, it can be used for classification. It can be used for binary classification, or it can be used for multi-class classification also. Similarly, it can also be used for regression. So what is regression? Regression, if you remember, is a problem where the label space is real. In case of classification, the label space is discrete. It may be binary or it may not be binary. So the cat dog classification problem is a binary classification problem because the label space has only two values, cat, dog. In this case of rating prediction, the label space has 5 values. That is 1 star, 2 star, 3 star, 4 star, and 5 star. But what if instead of trying to predict the exact rating which a particular customer will give to a particular product, what if I am interested in the average rating, right? So like if we consider say like these Amazon, the websites like Amazon, you will see something known as average rating. Like if you look at this is booking.com, where different people give ratings to hotels on a scale of 10. That is, they can give either 1, 2, 3, 4 up to 10. So here you can see that a value is shown, which is the average of all the ratings which different people have given. So as you can see, 195 people have given ratings, and the average value of all those ratings in this case is 7.2. In this case, there are 27 ratings. The average value of them is 6.3. So obviously, this average rating is a real number, right? Because like the average of like even if the actual ratings which the different people have given are discrete, in this case 10 values are possible, but if you consider the average of any reviews, that is of course going to be a real number. So now suppose instead of focusing on only one customer, suppose I am trying to predict what is going to be the average rating of a product, either on a scale of 10 or in a scale of 5 or whatever. So that's going to be a real number lying in that range. So that is a problem of regression. Now this kind of a decision tree can also be used for regression. Of course, there are other ways of regression also, but this decision. But since we have started with decision tree, let us carry on with it, and let us see that how decision trees can be used for regression. Okay. So here. Suppose we have got a decision tree somewhat like this. So, so how exactly we build this tree, or how exactly we chose this? Okay. So first of all, so what do you think will be the problem if we try to use this decision tree algorithm to a regression problem where the different labels are real values? What do you think, or what changes do you think I will have to make, or what are the points at which my existing decision tree algorithm will face some kind of an obstacle?
It will contain like a lot of uh, deep decisions trees, like deep branches.
Deep branches. Okay, fine, but before coming to deep branches, that is to say, even for creating one branch, that is for even the first split, will we encounter some challenges?
At the
The first,
leaf, I think mode will not be useful.
right, true, very true. Mode, like at the least, mode will not be an useful thing to choose. Why will it not be a useful thing to choose?
Because the data is real numbers. So
Right,
it's a very small there's a very small probability that we will see it even repeating more than once, like
ex-
one particular value.
exactly. So in such a situation, what can I do instead of mode? What can I choose?
So
Uh,
mean.
in,
Hmm? Sorry.
mean
Need, right. So, like in case, so typically that's what we do in case of a if you are trying to do the regression. That is as you very correctly pointed out, it's not likely that like we will see any single value being repeated more than once. But we may see some kind of that is to say, basically we will not have a probability mass function. Instead, we will have a probability density function. So what we can do is we can choose the mean of the or the expected value of that kind of those values. So that's definitely something we can do. But so that is definitely a good point. Apart from that, any other point? What is the first step? The first step is to calculate the maximum information gain. Now, to get the information gain, what we need to calculate is the entropy. Now, in calculating the entropy itself, will we face some trouble? Look at the definition of entropy. This is the definition of entropy. Will I be able to calculate if the defined values are real, then will I be able to calculate this quantity?
It will be like very low always because pi is very low.
Just continuing the previous comment, so like we can understand that there will be no single value of the of that variable which will have a particularly high value of pi. Right? So that is to say this particular definition is suitable for PMF and probability mass function. And probability mass function is what you associate with a discrete distribution. If whenever we are considering a continuous distribution, then what do we consider instead of PMF? What do we consider?
PDF.
density.
PDF. It is probability density function. So either we will have to redefine a concept like something known as that is redefine entropy for using probability density functions instead of a probability mass function. That is either we need a we need a different definition for the entropy using integration and the PDF and values of probability densities, or we have to use some other measure of instead of entropy. So, so what people often do is they build instead of going for entropy, what they try to go for is simply the variance, like the variance of the different levels. So, like variance, like you all know what is variance. That is, variance is like the square of the standard deviation. So what a measure of so what is variance? Variance is a measure of dispersion, right? So in a sense, what your entropy was giving you is also a measure of dispersion, right? So what's entropy? And like entropy is the different values you have got in case of entropy is basically it's related to the relative frequencies of the different values of the levels. Say in a cat dog classification problem, cat has frequency 0.7 and dog has frequency 0.3. Okay, so you are basically when you are calculating the entropy, you are basically what you are doing something similar to calculating the dispersion. in one case, it's like there is a 1-0 case which has a high dispersion. That is, this value is very far from this value. Then there is the 0.5 case which has low dispersion. That is, the two values are exactly equal. And this is 0.7, 0.3, which has medium dispersion. That is, the two values are reasonably far away from each other. Now, instead of that, suppose I go for like a real value. Let us say that different values are something like say 1.1, 1.3. Sorry, let me just for clarity, let me write it as something like this. Let's say that this is the full data set with 200 elements. Of course, all of where y is a real number. So obviously all the y's will be different. That is, no two y's will have exactly the same value. So these 200, now suppose on the basis of a feature, let us say C1 and C2. C1 and C2. Okay, so let us say, or let us let us specifically consider the case of hotel rankings, the average ratings of hotels in Booking.com. So let us say that there, like we are considering a hotel, that is like we have seen 200 examples of hotels which have got different average ratings, which lie in a range of 1 to 10. Okay? It can be any real number lying in this range from 1 to 10. Fine. So now the question is that on which are the features of the hotels that helps us to determine whether it's going to be the rating or what the rating is going to be. Now suppose like one rating is the whether it is and whether the rooms are AC or the rooms are non-AC. So AC and these are non-AC. If you consider the AC wala hotels, let us say that 70 of them are AC and the 130 are non-AC. Now, now you have to, and you also see that you look at the different ratings which the AC rooms have got, which the AC hotels have got, and you see that that is the values are the typical values. Of course, I cannot write all 70 values here, but here are some typical values which I am showing. Say like 1.1, 1.6, 2.3, 3.7, 4.9, 5.8, 7.9, etc. Fine. These are some of the typical values which we see in the AC wala hotels. In the non-AC wala hotels, you see that these are some of the typical values: 4.7, 5.1, 4.3, 4.5, 6.0, 5.5, etc. So, on the basis of these, what are your comments?
The AC hotel, they have a very large variation. Like it
Right.
varies from 1.1 to nearly 8, while that sticks nearly around 5. So.
Right. So like so regardless, so in which case is prediction easier? If I want to predict the average rating, in which case is it easier?
Non-AC ones.
Non-AC, because all the values are roughly in this region, in a particular fixed level. So everything seems to be lying from say 4.3 to 6.0. See, they are lying in a small range. In this case, it can be as low as 1.9 or it can be as high as 1.1 or as high as 7.9. Okay. So can you so what is like? Can you identify any mathematical quantity which will be say low in this case and high in this case? Like earlier we are looking, yeah, variance. So like this one has low variance or low standard deviation. This one has high variance or high standard deviation. So in the previous case, when we are dealing with discrete examples, we saw that having low entropy is useful rather than high entropy. In this case, we are saying that having low variance is useful rather than high variance. Right? So because high variance means that there is a much that is the target value is taking is from a much wider range. So it is very difficult for me to pin down a single value where I can make a prediction. In this case, since the variance is less, that means that target variable has a much smaller range. So if I take something like if I just say 5 as my prediction, I am not going to make a large error in any case. But in this case, if I take the value of say 5, I can make a very large errors, whether it is on the smaller side or on the larger side. Right? So this is probably a situation where I can make a prediction right away. But in this case situation, I cannot make a prediction. So what I have to do, I will have to try to split this list further. So then maybe instead of AC, we will have to ask for some other features. Maybe we have to look at its price. Is the price low or is the price high? And it may turn out that if the prices are like if it has low AC, it has AC and it has low price, then we see that there is getting ratings in the range, say 6.2, 6.5, 6.9, 6.6, 7.1, etc., etc. On the other hand, if the price is also, if the AC is there but the price is high, then we are again getting ratings like 1.1, 1.6, 2.3, 3.7, 7.9, 8.5, etc., etc. Okay. So fine. So that means if in this particular subset here we see that the variance is low or the standard deviation is low. So here I can make a prediction right away. And as someone already said that the prediction I can make in this particular case can be a mean of these levels. So that mean is obviously going to be something like let's say 6.5. But here this subset still has high standard deviation, right? High SPP. So I still cannot make a prediction because whatever value I predict, there will be a large margin of error. So I don't want to predict that as yet. Maybe I will split even further on another set of features. And then maybe after this splitting, then maybe I will decide to make the prediction. Okay, so basically this is the way in which you can use this concept of decision trees for regression also. Okay. So this this is the way in which we can use the decision tree both for prediction, both for classification as well as regression. In case of regression, this is what we do. That is, we calculate at every stage, at every subset, we calculate the mean value of the rating as well as the variance of the rating. And instead of calculating instead of calculating the information gain, what I calculate simply is the reduction in variance. In the same way as that is, I calculated the information gain. So my initial variance without splitting was 1.1. Okay, so 1.1 minus the variance, the weighted variance after splitting. So it turns out that after if we look at company C1, the variance is 1.5, which is higher than original. But if you look at company C2, then the variance is 0.5, which is lower than original. And we have to keep in mind the relative sizes of the two fractions of the two subsets. So this is the company C1. This accounts for 54% of the examples. So I multiply its variance by 0.54. In this case, in case of C2, there are 46. So I multiply its corresponding variance of 0.5 with 0.46, and I receive the reduction in variance that I observed, which is 0.06. Now, if I consider a different feature, like say this video rate, then it turns out that in one case, I get that is if the video rate is less than 30 frames per second, it turns out that my mean rating is 3.1 and the variance of the rating is 1.2, which is not not very different from what I had originally. But for those cases where the frame rate is above 30, we see that the mean rating is much higher, around 4.5, and the variance is also quite small, which is 0.4. That means that basically tells us that if the video rate is high, then most likely the camera will get a high rating. Okay, that is, the mean is quite high, 4.5, and the variance is also quite low. That means all the values are roughly around 4.5 only, give or take a few. That means what? That means I am more or less confident that a video with more than 30 fps frame rate is going to get a high rating. In case of videos with lower frame rates, I cannot say anything. Okay, so it turns out that if I calculate the reduction in variance in this case, if I do the calculation, this is the reduction in variance which I get 0.14, which is higher than the which is actually much higher than the reduction in variance which I got in this case, right? So I will go for this feature. I will split with respect to this feature. But that is compared to company, this frame rate seems to be a better feature for first level of splitting. But note that if, for those cameras for which the frame rate is more than 30 frames per second, I have got a very high prediction accuracy. But the same cannot be said with the larger set of cameras for which the video rate is lower. So here I still have a fairly high variance, 1.2, which is in fact higher than what I had originally. So what do I have to do now?
Split it further.
Split it further. So like I need not split these further. Only these I may have like again try to split further on the basis of what? On what basis will I split this further?
It can be
yeah.
Can be company wise.
So I mean not necessarily in anything. So again you evaluate the different features. Again you evaluate the different features. Again you evaluate different splitting. See which split gives you the highest for this subset. Whichever, if that is company, then find company. If it is something else, then go with that something else. So that is like at every stage, we will have to recompute this reduction and variance, and then only we have to proceed accordingly. Right. So that is but if you are going for a regression sum, that is if you have to stop at one level of prediction, this is how you will have to do. So this is your route. So like either you split with that is split on the basis of the frames per second. Sorry, not 300, 30 frames per second, or less than 30 frames per second, or greater than 30 frames per second. If this one, then your prediction is going to be the mean value, which is 4.5. In this case, your prediction is going to be the mean value, which is, again, sorry for the typo, it's not 3.46, it is 3.1. Okay, but of course, like if it is a regression sum, then this is where you will stop. If there is a regression tree, we will split this one further until we can get more, like, and we will continue splitting till you are getting more and more reduction in variance. This is basically the story of how you do regression with the help of decision tree. So what is regression? So just to recapitulate what all we have learned so far. So we started off with classification. Classification means what do I mean by classification? What do I mean?
From a function from the feature space to the class space.
A function from the feature space to the label space, fine. But so this is just supervised learning. This is not classification. This is supervised learning. Now classification is a subset of supervised learning. But like when do I call supervised learning as classification?
So when the target label is discrete.
When this label space is discrete, then I go for classification. Now this discrete may mean a binary also, or it may not mean. Like binary classification is a special case of classification, but it need not be binary. So what is the first algorithm we learned related to classification? That was k nearest neighbor.
K nearest neighbors.
So, and the second algorithm we learned is decision tree. Decision tree. So, k nearest neighbor, we saw various different variants. What's the variant? So, for example, different values of k are possible. Similarly, another variation is that instead of treating the different nearest neighbors equally while taking their vote, I can consider their weighted distance, their inverse distance from the query point as their weight. Right? So that is there is k nearest neighbor and decision tree. These are the two algorithms we have learned for classification. Now, of course, in case of k nearest neighbor, what are the choices to be made? The choices is one, value of k. The second choice is weight of different neighbors. How to weigh the different neighbors? In case of decision tree, what are the choices which we have to make?
Finding the discriminating features.
That is to say, basically how to find the discriminating features, or basically what criteria to use. Like, should we go for information gain, or should I go for Gini index, or should I go for something else? That is a design choice which we have to make. Secondly, the second choice I have to make is which splits to evaluate. As I said earlier also, like the number of ways in which the features can be split, that can be arbitrarily large. If the features are real value, then it's actually infinite. Even if the features are discrete, then also the number of splits can be quite large. So which splits to consider? We cannot evaluate all splits. Which splits to consider? So that's also a decision choice which you have to make. Thirdly, the depth of the tree, or the height of the tree. At which point should I just stop? Or rather, the threshold of the information gain. So someone was asking at one point that when do I decide when at which point there is no further information gain? Information gain will never become exactly zero. It will become, say, 0.1, 0.01, 0.001 or something like that. So at what point or what should be the cutoff value below which I will stop? That is again a choice which you have to make. So these are the choices you have to make in case of k nearest neighbor. These are the choices you have to make in case of decision. In case of k nearest neighbor, what is the biggest disadvantage?
Sir, we have to compute everything every time we want to make a prediction.
The testing is inefficient, because basically we have to calculate, that is you will have to compare the test point with all the training examples, unless we make some kind of special arrangement like that also we briefly discussed. But so basically the testing phase is expensive, right? So that is a problem of the k nearest neighbor. like in case of decision tree, is the testing expensive?
No, sir.
It is not at all expensive. In fact, testing is very easy. You just have to evaluate its different features one after another. You know which features to look for, and accordingly you take take a decision. In case of decision tree, testing is really quick, but the training is more expensive because you will have to consider so many different features. So you have to potentially consider all different features. You have to consider a large number of streets. So here, in case of decision tree, it's like training expensive. Training expensive, but testing is almost free. In case of k-nearest neighbor, training is absolutely free. That is, you hardly do any training at all. You just whatever data points you have, you use all of them for your you use all of them for your purpose. Of course, like some variants we discussed last week about how some of the maybe some of the outliers can be thrown away, or some kind of clustering can be done to group them together. Such things can be done, but that's not the vanilla k-nearest neighbor. Either way, the testing is relatively, the training is relatively straightforward in k-nearest neighbor, but the testing is expensive. The exact reverse is true in case of decision tree. The training is expensive, but the testing is really. Okay, so these two things, in a sense, are k-nearest neighbor and decision tree, in a sense, are complements of each other. Once the strength of one is the weakness of the other. The strength of the other is the weakness of the first one, and so on. And we also saw that these can be we saw how this decision tree can be generalized to regression also. So we will from next class we will see how to do the regression. We will see some example, some specific examples from regression in the next class. Before that, let me make an announcement. So tomorrow we have the lab. So if you remember that in the last lab class on last Wednesday, I had told you that we are going to use a particular platform which has been developed in our center for our coding assignment, and we will give a demo about how to use that platform. I said we will have that demo on Sunday, but by Sunday that platform was not yet ready. Now it is ready. So tomorrow during the lab hours, we will first have the demo session. The TAs will give you a demo of how to use that platform, and after that we will have the assignment. We will give you the assignment, and we will give you time to solve it. You don't have to finish the assignment in tomorrow's class itself. You can take time till next Wednesday, and you will have to you complete the assignment and submit it following the instructions that will be given tomorrow. And our first test, which according to the institute rules has to be done during 6 to 9 September. We will have that test next Wednesday, which is going to be 8th of September. So today is 31st August. Next September, next week, next Wednesday, which is 8th of September, we will have our first class test, after the lab session. The lab session will be we will not utilize the full 3 hours of the lab session. Maybe in 1 hour will be enough for whatever demo that we have to give. After that, we will have the class test. The exact form of the class test I will tell you early next week. The syllabus for the class test will be up to what we have covered till today. That is k-nearest neighbor, decision tree classification, decision tree regression, and general and supervised learning, feature selection, etc. in general. Okay. Fine. So with this, we come to the end of today's class.
Hello, sir.
Yes.
So, can we get an idea of what kind of questions will be asked in the test?
Yes, I will